This video is on section 8.1, exploring exponential models. In this section, in video, we will define what an exponential function is, how to identify exponential growth or decay, and then later, in a second video, also how to write exponential functions. What an exponential function is a function that has the general form y equals ab raised to the x power, okay? Where x has to be a real number. Okay. Again, an exponential function is a function that has the general form y equals ab to the x power, where x has to be a real number. A couple of restrictions here. We have to place a couple of restrictions on our values of a and b. A cannot be 0, b has to be greater than 0, and b cannot be 1. So an exponential function is a function that has the general form y equals ab to the x raised to the x power, where x is a real number, and the following restrictions apply. A cannot be 0, b has to be greater than 0, and b cannot be 1. One other bit of terminology that we have to understand before we actually go ahead and graph an exponential function is what it means to be an asymptote. An asymptote is a line that the graph of the function approaches as x grows to infinity. So now let's go ahead and graph one of these exponential equations, or exponential functions. We have the function y equals 2 to the x. Now what we're going to do is we're going to graph it by simply picking points. So all we're going to do is wherever we see an x in our function y equals 2 to the x, we're going to replace it with the value that we chose. So in this case we have a -3, so we're going to say y is equal to 2 to the -3rd power. Well, remember back in chapter 7 what that negative exponent does. It takes the 2 to the -3 and rewrites it as 2 to the 3rd. And when we evaluate 1 over 2 cubed, we get 1/8. Likewise, for x is equal to -2, we have 2 to the -2 power, which is really 1 over 2 squared, which when evaluated, it's 1/4. Same thing for 2 to the -1st. 2 to the -1st is simply going to be 1/2. Plug 0 in. 2 to the 0 equals 1. Plug 1 in. 2 to the 1st equals 2. 2 to the 2nd power. When evaluated, it's going to be 4. And 2 cubed will give us a value of 8. So we have the table of values now. -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. If you want, you could think of them as ordered pairs. -3, 1/8, -2, 1/4, and so on. So you have -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Now what we're going to do is we're going to take all these ordered pairs that we have and we're going to graph them on a coordinate plane, and we're going to see what happens. So now using those ordered pairs that we just calculated from the table, we'll plot them. We have 0, 1, 1, 2, 2, 4, 3, 8. We also have -1, 1/2, -2, 1/4, negative 3 1/8. Now it's a matter of just connecting the dots with a line, the points with a line, and extending them. Just like that in both directions. And that's what the graph of y equals 2 to the x will look like after we plotted the points into our nice curve. You're probably noticing that as x grows in the negative direction, you're never really going to touch the x-axis. You're never really going to get a y value of 0. And that's because no matter how small your x value is, you could have x being negative 1,000. When you take that negative 1,000 and plug it in for x, you're really going to get 1 over 2 to the 1,000. Again, there's negative 1,000. You plug it in for x, you get y equals 2 to the negative 1,000, which is the same as 1 over 2 to the 1,000. This value here is incredibly close to 0 without being 0. So no matter how small or large this value of x is, you're never going to hit y equals 0. You will never have a y value that's 0. So in this case, as x grows to negative infinity, we're going to grow closer and closer and closer to y equals 0 without even touching that. That is what we call a horizontal asymptote. It's a line of the graph that the function approaches as x grows to infinity in either the positive x direction or the negative x direction. In the case of y equals 2 to the x, our graph is growing closer to y equals 0 in the negative x direction. So our horizontal asymptote is simply the line y equals 0. And that's the graph of y equals 2 to the x. So right now, what we've done is we've learned what an exponential function is, and we've graphed an exponential function. Now what we're going to do is we're going to identify exponential growth and decay. But first, we have to understand what it means to be a growth factor or a decay factor. And that all hinges on the value of b. If our value b here is greater than 1 in the function, in the exponential function y equals ab to the x, if our b value is greater than 1, then b is called the growth factor. So if our value of b in our exponential form y equals ab to the x is greater than 1, then b is called the growth factor. Now if our value of b is greater than 0 and less than 1, b is then called the decay factor. So if b is greater than 0 but less than 1, then b is our decay factor. So if I gave you the two functions y equals 4 to the x, we're looking to figure out, does that model exponential growth or exponential decay? Well, if you look, remember what it means for exponential growth, our value of b has to be greater than 1. In this case, our value of b certainly is greater than 1. So y equals 4 to the x models exponential growth. Likewise, if I gave you the function y equals 1/5 raised to the x, that one, our value of b here is 1/5, and certainly that is greater than 0, but also less than 1. So this one would model exponential decay. So now we've done a couple of examples. Let's actually do some graphing, some more graphing. Let's go back to graphing some functions just by picking points, just for some extra practice here. So to this point, we've learned how to graph the functions, horizontal asymptotes, cut. Right, so to this point, we've learned what an exponential function is, what an asymptote is, how to graph an exponential function, and how to identify between exponential growth and decay. Now let's go back to what we originally started with and graphing these exponential functions. And we'll do 2 more examples of how to graph these exponential functions. So here's the first extra example here. It says graph y equals 3 to the x just by picking points. So I have the points here, x of -2, -1, 0, 1, and 2. Remember, just plug the -2 in for x. So you get 3 to the -2. That equals, remember the exponent rules, that makes it 1 over 3 squared, which makes it 1/9. Same thing for -1. 3 to the -1 equals 1 over 3 to the first, and that's just 1/3. 3 to the 0, all that's going to give us is 1. If you raise something to the 0th power, we always get 1 back. 3 to the first is going to give us 3. And 3 squared gives us 9. So now we're going to take all these values, -2, 1/9, I'll write it as an ordered pair. -2, 1/9, -1, 1/3, 0, 1, 1/3, and 2, 9. So those are our ordered pairs that we will graph on the graph. We have our function y equals 3 to the x, and we just found the points that we're going to use to graph it. So remember, we have the point 0, 3, or 0, 1, 1, 3, 2, 2, 9, -1, 1/3, -2, 1/9. And if we wanted to evaluate it at -3, 3 to the -3rd would just be 1 over 3 squared, 3 cubed, which would give us 1/27th, which is pretty close to the x-axis. Connect the dots, draw a line. Just like that. And if you notice, as x gets smaller and smaller and goes from -4 to -5 all the way down along in the negative x direction, as we pick values of x that are smaller and smaller, like -100, -1,000, you're going to get a very small value that really isn't 0. Well, this graph is going to approach the line y equals 0. It's never really going to actually touch it. So in this case, like our last case, y equals 0 is our horizontal asymptote. Right, so now we have the second example, extra example here. We have graph y equals quantity 2/3 to the x just by picking points. Right. So if we plug our -2 in for x, we get 2/3 to the -2. Remember that -2 distributes to both the numerator and the denominator. So we get 2 to the -2 over 3 to the -2. A negative exponent in the denominator brings that to the numerator, and a negative exponent in the numerator brings it to the denominator. So So these two will just flip and become 3 squared and 2 squared, which will give us 9/4. Likewise for -1, we get 2/3 to the -1 becomes 2 to the -1 over 3 to the -1. These will flip because a negative exponent in the numerator and a negative exponent in the denominator. 3 to the first over 2 to the first, which is just 3/2. Plug in 0, 2/3 to the 0. That will just give us 1, because anything raised to the 0th power will give us 1. 2/3 to the first power will give us 2 to the first over 3 to the first. The exponent distributes to the 2 and 3, and we're left with 2/3. And finally, x equals 2. 2/3 squared. 2 distributes, so we get the 2 squared over 3 squared, which gives us 4/9. So through finding all those points, we have our ordered pairs: -2, 9/4, -1, 3/2, 0, 1, 1, 2/3, and 2, 4/9. And using these points, we will graph the equation of the line. So now let's graph our function y equals 2/3 to the x using the points that we just got. So we're going to all automatically have 0, 1. Go in the negative direction, we have -1, 3/2. -2 will give us a -9/4. So that'll be roughly about there. Go to the +1, we get a 2/3. And on the 2, we get a 4/9, which is right around there. If you want to choose an extra point, we'll choose -3. If we evaluate it, we get 2/3 to the -3, gives us 2 to the -3rd, all over 3 to the -3rd, and that gives us 3 cubed over 2 cubed, which is 27 over 8. And that's going to be right around here, that will be. We want to evaluate it at -4. We certainly can. And just get 2 to the -4, all over 3 to the -4. And we would get, because of the negative exponent in the numerator and the denominator, they would split. And we'd get 81/16, which is roughly about 5. A little bit greater than 5. If we keep going in the positive direction, 2 over 3 cubed gives us 8/27, just somewhere down here, and we can graph the line quite easily. And in this case, as x grows to positive infinity, you'll notice that we'll get really, really close to the line y equals 0, but we will never touch it. So in this case, our horizontal asymptote is just y equals 0.